Okay, thank you.
Mhm. So we'll start with more people are jumping on. We'll get about 26. Um, any questions about anything? As a matter of fact, let me do one thing. I've got a secure CRT thing so I can use MATLAB. And where is that? Now I can get hopefully get MATLAB on here. I'm thinking about using Octave more and more, just because it eliminates the need to get this FlexLM license. All right, questions? Anybody? I saw people had 2 tests. Who has taken a test so far using HonorLock? Anybody?
I have.
All right, how did it go? Was it all multiple choice or how did it work?
Yeah, ours is all multiple choice.
Well, mine is not going to be on multiple choice. I mean, if that's the provision that has to be on multiple choice, then I'm not going to do it. By the way, I still haven't gotten there. Talk to him, so I haven't do it today. But did anybody ever else have a test without that where it was written answers, you know, written work that was submitted? Anybody?
I took an econ test, which is all usually written in math work, and he changed his written math work test to multiple choice as well on HonorLock.
He changed it to just multiple choice, did you say?
Yeah, and like our test used to be all like math and handwritten out, so I don't know if HonorLock, you know, if he did that because of HonorLock or.
Some of you are taking a test by Dr. Wentworth, aren't you? And as you're taking a analog test today, is that right?
No, that was for econ.
What's that?
That was for engineering econ.
I know, but is there somebody taking Wentworth's analog test today or not?
I think that analog test is right now, and I don't think any of us are in it.
Oh, I'm sorry. Okay, I got it.
No, Dr. Bashir has given us a EMAG test, and he sent us a PDF of the test earlier this week and has it due on Friday.
Oh, it's a take-home? Okay. Usually those can be much more difficult.
I was going to say for power as well, Dr. Gross he's sending an email in the morning at class time and then making it due like an hour after class time. Like you send it back to him as a PDF.
I think I'm gonna just use Dropbox. I think I can do a time limit on there. Is that right? Can't you on Dropbox have a certain window start, window stop for the assignments to be handed in? Isn't that right, or am I wrong?
I'm not familiar with it, so I wouldn't know. But
Y'all, you've been using. I mean, sorry, not Dropbox. On Canvas, they have something where I can open an assignments window for when you can pause it assignments. I can like have it shut off at a given time. Isn't that right?
Yeah,
Yeah.
my thermo professor is doing that for my thermo test tomorrow. Like we're going to have like a multiple choice section and then a turn-in assignment. Like the turn-in assignment is going to be like a PDF of our work, while the multiple choice is just our answers.
I think Riggs is giving a test too. I'm going to talk to him and Stu to see how this goes. But what I don't want to do is have to do a redo of a test. What I'm thinking is this right now. I'll just tell you this. I'm thinking about a 2-hour segment, 2-hour window. I give the exam, you print it off, whatever you need to do. however you want to do it, but you get the actual exam in front of you. And then write on the actual exam, and then take a picture of it, and then send it to, take that picture, and I guess you'd have to manage it into a Word document or something like this, and then drop it off in Canvas. But 2 hours should be plenty of time for an hour test. So you take care of all the technical bugs. I think that's, in my estimation, that should be fair. And
Yeah, that seems fine.
I think that would be fine.
Yeah,
I don't have a printer.
I'm sorry, what?
Yeah, the only thing about that is I also have a class right after this, and I know a couple other people do as well.
Yeah.
Oh,
Also, I don't have a printer.
well, you can write down the questions, right? You got a
Yeah.
camera, don't you?
Yeah.
The real thing is this, if I have 4 specific questions and 4 spaces that I want things to fill out, and that, maybe 3 or 4 parts problem. You know how my tests are. I want to be sure that each problem is on a separate page if possible. Because what I do is I grade one, everybody gets the first one graded, and everybody the second one, and I usually separate them like that. I'll do that, and I'll probably make at least 2 different tests, maybe 3 or 4 different tests, but they will be representative material, and they're not going to be, I'm not going to do something crazy, but they'll be more difficult than typical ones without notes or without closed notes exams and no formulas. So I'm just going to level with you what I'm planning. Now, the next thing is, let's take care of questions. Does anybody have any questions? Nothing? Did you all do the assignment, or have you tried the assignments? I figured I'd get some.
Yeah, you went over it fairly thoroughly in like the video that you linked.
All right. I I was anticipating some questions, and this is homework 21. I think everybody, I'm looking at it right now. Matter of fact, let me pass the screen. Can you all see this here?
Yeah, we can see.
Yes.
All right, now that one was past due. I assumed everybody got that in, but I actually haven't scored that thing or anything. So are we all good with this as far as plotting with MATLAB and the DTFT of these things? These are basically right out of the tables, right? You could use properties or tables to get all of them. Any questions about these before I move on? Class.
Could you plot number, I think it was 5 in MATLAB? I was having some issues with that one.
This one, 5?
Yeah.
Right here? All right. I'm not going to spend a whole lot of time, but I think I can do it. So if I have MATLAB, and I'll pull it up. Let me pull up another window, and we'll do it from scratch because people are asking about MATLAB. They're unfamiliar with it. I'm just going to start from scratch. I always do close all, clear all, and then CLC. And the only thing that does is give me the actual command window will be empty. The command window is down here. It's the one with those 2/3 zeros. Then after that, I usually put constants down. Now for this one, is the magnitude 2? I don't have it open in front of me. Is that right? What?
Yes.
Was that a DFT, or you just want a plot of that thing? You just want a plot of this? You can do that. So then after that, I need to go ahead and create. Now I'm just going to create T. So T equals, and I use linspace. And now the first thing you do is say where you want to start. The next thing where you're going to stop. Did it say 5 seconds or something like that? I forgot exactly. And then the number of points. I'm going to literally put the number of points in. Now I'll put it as n. And I'll make n equal to, say, 2 to the 8th points. That's a lot of points. Then after that, let's see, I got somebody making a question. if the audio's messed up, I'm gonna put in my headset. Tell me if this helps. Is this any better?
Yeah.
I think it's
Yeah,
clear.
that seems a lot better.
All right, I'll use this from now on. Anyway, this is T, the lin space, and then I'm just going to say, could be X, Y, doesn't matter. X is equal to, it's really A times EXP, and then is it minus 2 times T? Is that right?
Yes, and you'll want a capital A there, I think.
Yes, you're absolutely right. Now that dot's important because these are going to be term by term multiplication, not matrix multiplications here. And so then I take that and it's times a cosine, and was it 10t?
Yes.
And that really, after that, that's right. Now I'm just going to do a plot.
I think you're missing a multiplication sign after your
I did.
dot.
I am. Yeah. It's a dot star. Thank you. Then I'm going to take plot of t, comma, and then x. And I'm going to do a couple things here so everybody has that. I'm going to put, let's say, x label. And when you do a label, you use a single, it's just a simple apostrophe and say what you want. And the x-axis is going to be just x. The y label will be time in seconds. And then you can put a legend. And I don't know if I have to put that. And then a title if you want. Just plot of x, give this that. And then grid on it. The simply thing, I'm trying to put as many commands down as possible. The grid on does one thing. It gives us a hash grid, and you can make it at any resolution you want if you look carefully in MATLAB. I'm going to run this. Hopefully there's no problems. I'll call this, this is 325. Save it, and then run it. And did it come up there? So that's it. You asked, who asked this question?
It was me.
Is that good enough for you?
Yeah, that's good.
All
Thank
right, sure. Any other questions about MATLAB or any of the homework? All right, we're done with that then. We'll go to homework 22. And here, now this is the comparison of the FFT output to an actual Fourier transform, right? Can you all see this, class?
Yes.
I'm
Yeah, I can see it.
all right, I'm making sure, trying to be able to see you guys too. All right, good. So if we want to do this, the thing I think I said, but I'm going to, it's in this lecture right here. Did y'all watch this lecture, class?
Yes.
All right, now I did the comparison, right? But I'll just state it again, and I'll try to do it down here. So if you have x of k, and that is the FFT of x, we'll assume that. Then if you want to compare directly to a Fourier transform, your x of Fourier transform would be, and this would be the omega value would be equal to the effective omega value.
And so if you're going to take a DFT and you want to directly take it and turn it into something that would be the Fourier transform of that, if it was sampled fast enough, here's how you do it. You would let omega, and I'm going to use W, omega equal, and you start by it's 2, and then it's going to be times pi. Then you divide that by n, where n's the number of points, right? Now the next thing you have to divide it by is 1 over t sub s, and that's your sampling interval. So now I've scaled this thing. Then after that, I'm going to go ahead and multiply this by k, and that's the integer. By the way, I have this. I'm trying to think of where I have this. This is right here in the what I'm doing here. So then I take this right here. This is what omega will be. And I say this will be the equivalent transform if I take my omega value. Maybe I should actually put omega there so I don't confuse people. If I had a Fourier transform and instead of using just omega, I replaced it with this, I would get the Fourier transform of the signal, but for the specific frequencies that are associated with the adjusted DFT. And I'll do this example. So now what is that equal to? It's equal to 1. You have to do this minus 1 minus exp to the minus, and it's going to be 1j times, or 1j times, now it's going to be this omega right here times ts. So what I do is just take this, hopefully I can do this, and I'm going to get rid of the ts because there's a ts multiplying that. I'll just put a 1 in there. All right, and then have to group that. And then it's divided by 1j. Come on. And it's that thing again. Then I take this whole thing and I multiply it by x of k. And then they'll be directly comparable. Now, it seems like a headache, but let me show you. All right, if you haven't done this, I'm going to show you what I mean. I'm going to take this code right here and go into the MATLAB, and let me get rid of all this for now. And now, here, I'll tell you what I'm up to. Here, I've got 2 to the 8th points, 256, I think. So I have this. I'm going to go ahead and say that TS, the sampling rate is 10 over n. So it's a 10-second interval that I'm going to use. And I'm going to chop it up. Actually, what I can do is this. TS is right here. It's 10, the length divided by n. So that's my TS that I need. Then I take this. Now, if you look at this, the minute I take this and I make it discrete values, and then I get discrete values of here, this signal, right here. Now, this is like a data stream that you would use to take a DTFT or DFT of. So I do it right here. I take the DFT of it right there. You follow me on this? This is just the fundamental definition of the DFT right here. Now, after that, I go ahead and I create these frequencies that I said, and you take 2 pi divided by n divided by ts times some index. You can use k or I, it doesn't matter. So I'm going to create these frequency points. Then I'm going to also, when I do that, I'm going to say that now the actual Fourier transform versus I is right here. That's just, you know, if you have, this is e to the minus 3t u of t. Well, that turns into be 1 over 3 plus j omega, right? Y'all agree with that? That is the Fourier transform. If you just have e to the minus 3t, this is the Fourier transform of it. So I'm going to take this Fourier transform and I'm going to compare it directly to the adjusted DFT so we can directly compare it. So I take the DFT, the x of k, and I multiply it by this right here. That's what I just did, times x of k. And then I'm going to plot them and see how close they are. All right? You all see this? What this is what I've done down here, right here. With me?
Yes.
All right. So now I go ahead and hopefully I didn't make a mistake, but I
Do
did.
you have to clear line 4 or delete line 4?
Yes. Yes, I do. All right. You see how close they are? Everybody?
Mhm.
Almost exactly the same. Now, watch what happens when I increase the number of points. What if I go 2 to the 10th? If you can tell the difference, I'll be surprised. You might be able to, but I don't know. You see how they're virtually the same thing?
Yes.
And you can also home in, if you just want like the x-axis, this is actually the value of omega. So what you're seeing here, if I can get that plot back up. What you're seeing here, this is the real frequency domain transform of that. But a lot of this stuff is really information that's kind of unimportant because it's way out, it's almost zero. So if you want to home in on the actual, the main part of the signal where it is, you can go over here and you can say, you can have X limit and you can just go from say 0 to maybe 20. And now, if you do that, and I can just, if you highlight something and hit F9, it executes it. Now, if you look at that, you can see, there's a little bit of difference. Little bit of difference right there. Let me see if this changes if I go to 10 to the 12 points. What is that? That's 496, isn't it? 4096. Still a little difference. In the limit, as you actually take a, allow the points to basically go to a, say 10 to the 18th or something like that, a huge number, these two will asymptotically approach each other. Okay? Everybody with me? So that's taking a DFT and adjusting it so it can be directly compared to a Fourier transform with a signal. And what I really should say is this, in radar processing, what you want to do is scale everything so it's understandable. Now, I'm very familiar with Fourier transforms. The DFTs, I don't know what the DFT of a lot of signals look like, but I know the Fourier transforms of decaying exponentials, the Fourier transforms of like a decaying exponential times a cosine of omega naught t, or a pulse function times cosine of omega naught t. I'm very familiar with that signature. So if I adjust the actual, if I take a signal, they sample in radar, you're going to take maybe 10,000 points. You're going to store it, and then I can look right away in the frequency domain, and I can see if there's information there of interest. For instance, if there's a signal, a strong signal at a certain frequency, then I can go ahead and plan ahead based on that. That would be like a jamming frequency that's coming in unintentionally. All right, kind of get an idea of why we use this stuff. This is going to be real-time data processing, but you have to take a snapshot in time. So I listen for like a millisecond. I basically take that and I'm sample it at extremely high rate of speed, then I store that information and I do signal processing. And this is a way at least to get an idea of what's out there in the frequency domain. By the way, if we did this, let me do one other thing while we're on it. Let's go ahead and take this and multiply it by cosine. Take a look at a difference, all right? So we're going to take this and multiply by cosine of, say, 20t. And I need to get rid of x limits. Let's make them out to 100. See what goes on here. Now, when I do that, well, the first thing's not, I didn't take this and take the cosine of omega naught t of that one, but you can see right here that what we have is, we have a strong frequency presence of about 20, or 20, right? Yeah, close to 20. I'm not sure if, let me get it up to 200 and then get rid of this altogether. Let's see what happens. All right, you can see that this allows me to get a good idea, and this is what I would do with when I'm doing this. I would see, by the way, this right here, the thing way out there, that's an artifact. It shouldn't be there, and the reason it's there probably has to do with the number of data points I've taken. But this is a real signal. It's a strong one, and that's what I would see with if I was looking at the radar data when they do a first interpretation. If there was a strong signal there, I know that there's a transmitter frequency out there that's at about whatever it is, 200 radians per second. Okay, is this following me what I'm doing? Now, this is basically showing you how to take a DFT of any signal and adjusting it so you can take a look at the actual Fourier transform of that signal. There is one stipulation. Does anybody remember what the one stipulation was in order for this method to work? Anyone?
Doesn't it have to do something about the radius of convergence for the functions?
Not like that. The value of x of t has to be about the same as x of t plus ts. So the change in the values of x of t from one point to the other have to be insignificant. Now, there is one exception. Can you see right at 0, this thing's going to go when the cosine is going through a 0, right? At 90 degrees when 200 t is equal to pi over 2. Now you're going from a positive to a negative value in 3 points. Do you see that? All right. That's the one exception, and that will cause a bit of an artifact. Right? It'll cause a small change, and it may be the reason we're seeing that high frequency signal out there. I'm not absolutely certain about that. But all in all, this is a great method to use if you've got a signal. Suppose you have a raw data feed and you know what the TS is, and you're trying to figure out, what's the frequencies, what are out there? Well, you can use this method. You can go ahead and take the DTFT and adjust it like I've shown here, and then you can see spectrally where are the frequencies. Does it make sense? But it has to be sampled high enough. Just for kicks, let me show you what happens when it's not. Let's make 2 to the 4th point. That's 16 points, 2 to the 5th. Now watch what happens when we do a comparison, and I'm going to get rid of this. Now you can see there's a big discrepancy. And that's because the values of the sample are starting, if I look down here in the command window, of x of 1, I get that, and x of 2, that's a big, big difference. Do you see that? One is 1, the other is 0.3799. That's a huge difference, and that'll reflect in an error in the actual adjusted DTFT. Everybody good with that? All right, I'm trying to be clear. Now, can you just give me a thumbs up or something if y'all understand this and I can move on? Okay, I've got it. Okay. Any questions about this? Anything I've done so far? Anything? No?
So I do have a question.
Go ahead.
This process that you're taking us through, this is just sort of an application
Absolutely.
of what we'd be doing, because we can't take an actual Fourier transform of a real-time data stream. We have to take a discrete Fourier transform.
Yeah, and the way I build up to this, I start with Fourier transforms, right? Then I say, well, what if you have a sample data stream still infinitely long? Well, then you have a DTFT, right?
Mm-hmm.
Now, that DTFT still doesn't buy anything in terms of real-time processing. So now we take the DTFT and we talk about a limited number of data points.
Okay.
Sampled at a certain rate. By the way, the more points you get, the better this works. That's the bottom line. So now I have that. And what am I going to do? Well, I'm going to go ahead and adjust that. Now, this is me personally, because I would like to see how it compares to a Fourier transform. I've got a real good feel for Fourier transform business. I know what certain things look like. And I can definitely tell you what a pulse function looks like in the frequency domain. It looks like a sink, right?
Mm-hmm.
I know an exponential decaying looks like a 1 over omega plus j, or well, I mean 1 over whatever it is, a plus j omega. And I can more or less figure out what's there if I have the ability to directly translate that or turn it into something that would be the equivalent Fourier transform of that.
Okay.
That's the real bottom line on this.
All right.
And it's useful. I'm telling you, it's very useful. So next, because now you see the linkage between the Fourier transform, the DTFT, and the DFT, or really FFT. That's the linkage. Do y'all see that? Let's continue then. Next, getting back to the homework here. Now, part 1 of this homework. Here I have a simple a system of equation. And when it says Fourier transforms, what it's really talking about DTFT. Can you all see this right here? Anytime it's sampled, it's DTFT. They just Fourier transforms. For the first one, we might as well talk about these. And if you don't mind, I'd like to work through these to make sure everybody's okay with them. Good with that?
That sounds good with me.
Yeah.
All right.
Sure.
For the first one, this is a simple difference equation, right? It's taking the value of y of n minus 1/2 y of n minus 1, and it's equal to x of n. You'll notice there's no initial conditions to worry about, right? So what happens when we take I can't cut that out, but if I come down here, and what happens when I take the DTFT of that? That was y of n minus 0.5 y of n minus 1, right? And then it's going to be equal to x of n. This is about as simple as it gets. Do y'all agree with that?
Mm-hmm.
All right. Do the transform of that. So the transform of the first one would just be y of omega. And I'm going to just use w if you don't mind. All right. It's capital omega, but I'm just using that. All right.
Mm-hmm.
Let me go ahead and do this. So if somebody is looking at this later, they'll know. I'm going to say w is equal to omega. If you're wondering why I'm doing this, this is a LaTeX form of this. LaTeX is a symbolic, it's a language used by a lot of us for writing everything that's a technical document, because you can easily get all the mathematical symbols right at your keyboard. You don't need to WYSIWYG click things. With me? All right, so now coming down to here, that's that. Then what? Then it's minus 1/2, right? Times what? EX, or e to the what? You have your tables? I don't know which page in the book they are.
Minus j omega.
Yeah, but what page are the tables on this? The DTFT
I
table.
believe 396, but it could be a page or two on either side of that.
396. I think you're right. That's close. These are the properties. which is just as well because we needed that property. So it's going to be e to the minus, and it's j, and here it's going to be n omega naught. So, or n not, so it's just by 1, so it's e to the minus j, and this would be omega, right? Times, come on, times y of omega equal x of omega. Agreed, everyone? You can do it by paper and pen. So then if I factor out, I get,
You said x of omega, correct?
yes, sorry.
Not x.
My eyes are getting bad for doing these monitor things. So now I'm going to take x of omega and divide it by, y of omega by x of omega. And that is the transfer function h of omega. And that is simply 1 over 1 minus e to the minus j omega. Y'all agree with that? And remember, that's a capital omega in there, correct? So what is the impulse response if I asked you a good question on test, right?
I think there should be a 0.5 before the E.
Yeah, you're right. Absolutely right. That was my bad. So I'll put a 1/2 right there. So what is h of n, everybody?
1/2 to the n to the u of n, or times u of n, I mean.
1/2 to the n, right, times u of n. Y'all see that? People?
Yes.
Okay.
Yeah.
All right. That's the first problem. Pretty straightforward, right? The next problem is what? You find these values. Now, these are just cake problems. What's the first one right there? What is it?
Isn't it
1.
just the
1.
same thing? Yeah.
1. What about the second one?
E to the negative j omega.
That's right. This one here would be simply e to the minus j. Oh, gosh. E to the minus j, and technically it'd be omega, and in this case, just n naught. Oh. Right? What about the last one? You got this one, right? The next one is what? Speak up. Who's
1 over 1 minus 3/4 to the e, or 3/4 times e to the negative j omega.
Right, and you know what I'm going to do? I'm going to do this. Since this is going to appear all the time, I'm just going to copy and paste that sucker. And that would be right. Follow me?
Mm-hmm.
Everybody? All right, let's do this one. Because this is one. This is a high frequency signal I'm about to show you. A high frequency signal or a higher frequency signal. Now, what if I do this? If I made this 3/4 minus, what happens? Let me come down here and do it. Suppose I have a signal and I say x of n is equal to minus, x of n is equal to minus 3/4 to the n u of n. What is that one? Guys? Anyone?
1 over 1 plus 3/4 e
Yep.
to the minus j omega.
Yeah. It'd just be plus because it'd be minus a minus.
That's right. Right. Now we can keep playing with this and making it more and more difficult. What if I take that instead of u of n, I make it minus u of n?
Would that be plus j omega? E to the positive j omega?
No. Are you looking at, don't guess, tell me a property. If you look at property 5, time reversal, you see how, this is on page 395 if you've got your books. So let me do this. If it's time reversal, all right, anywhere there's an n right there, you would have a minus n. So if I say x of n, I'm trying to copy this. If I say x of n is, just make that a for now. Right? I know that that goes to agreed?
Yes.
Everybody? All right, so x of minus n, and I'm going to do this, x of minus.
Wait, wouldn't it be minus a?
Yeah, it is. It is. It is. You're absolutely right. I'll slow down. I'm trying to cover some ground here. So then this down here, come on. So when I have x of minus n, that would be equal to a to the minus n, right? Times u of minus n, right? Now that would do what? Then this would be plus, right? Look at property 5 in your book.
Yeah, that's correct.
All right. Now, if we had, let me try to, what is this right here? What is a to the minus n? Isn't that 1 over a quantity to the n? Class?
Yes.
You all agree with that? If you don't, believe me, you can always try it. If you have 2 to the, 2 to the minus 2, right? That's really 1/2 to the 2 power. Correct, class? You can go ahead and play with this and make sure you agree with me. Agreed?
Mm-hmm. Yes.
So if I wanted to do something, remember, I could take this right here. Let me just tell you about a couple things I can do. And I could take this and make it, I'm trying to do this for mine. Hold on for 1 second. I got a message that I got to take.
I'm gonna hop out for my next class.
Oh, I'm sorry. I'll get to that later. Let me ask you, did you have any other questions about this, what we're doing? Is that Ruth?
Yes.
You're the one that said that you had 2 tests and stuff, didn't have time. Is this
Yeah.
answering your questions?
Yeah, I think so.
All right, there's one last part to this before you jump ship. down here for this one, that's the impulse response. So to get h of omega, you have to take the transform of that, right?
Mm-hmm.
That's just an a to the n cosine of omega naught to the n problem. And that's in the book, I believe, that property. And I gave that to you too, I think. Yeah, that's on page 398, property 8. Do you see it?
Yes.
All right, that's how you do that one if you want to, but you can do it, you should actually go through the math on that. And then if you have this signal, this is important. You see where this signal is? It's cosine of pi over 2n, everybody?
Yes.
Here's the deal. That is it's simply a delta function at 2 points. That's going to be a delta function at plus or minus pi over 2. And when you take this h of omega for this one and multiply it by the h or the x of omega here, you'll see that this, right, that this actually will be reduced somewhat by this, this one's window. I don't have time for it today because you're leaving, but I wanted to mention that. Then the last thing before you jump, listen. How do we do these? All right. What is the one thing that we will use to do these?
Duality?
Duality, right. And what we'll do is take a look at this one. And first, if we just have a pulse in the frequency domain, we're going to get a sync in the time domain, right?
Mm-hmm.
It would be tau, and the width of tau here is pi, right? And then would be the sync of n times, sync of n tau over 2. I'm not going to do it right now. All right, well, you've got that. So now you have a function in the frequency domain going back to a function in the n domain. Well, if I multiply by omega, what happens if I multiply by omega or by n in one domain? In the other domain, you take what?
The derivative?
Right. And there's properties. You can do that for this one. And remember that capital omega is just like small omega now. What about the second one? What about this? What do we do? Well, if you have p of omega, p pi of omega goes to x of, some x of n, then if you put a phase difference in the frequency domain, you see that?
Frequency shift, right?
Yes, it's just multiplying by e to the j pi omega. And this property, if you want to know where it is, it's the frequency shift, it's third property on page 395. See it? People?
Yeah.
Okay. So I assume this homework you're pretty good with now. Ruth, are you gone or he here?
I'm still listening, but I'm about to leave.
All right. Well, you can go ahead and leave. Did that answer your questions about this homework?
Yes, thank you.
All right. Windowing. We got a lot of people here. If you got to go, go ahead. But I'm trying to do my best with what tools I have available to me.
I got a question for you, Dr. Baginski. In the video lectures, do you actually go over like how to derive some of these crazy functions by hand?
Mm-hmm. Sure, I do. If you watch, I posted the whole lecture series right there for spring last year, right? You can get all the lectures, can't you?
Yeah.
All right. Has anybody looked at any other lecture besides the one I've tabbed there? No? Well, the next two are very good. And they go ahead and they address a lot of natural concerns when we're talking about DFT and the DTFT, doing problems and filtering and things like that. So this particular one, the DFT and the inverse DFT, it's just basically giving examples, talks about some properties about symmetry. Here, it's computing the inverse DFT. That's on MATLAB, so nice. It's just IFFT. Did you all try that on MATLAB, by the way?
MATLAB has been running really, really slow for us. Like
I'll make a suggestion. Just go and use Octave. My radar class, several people are either using Python or Octave because of this problem with the university system. Does everybody know about Octave here, class?
Yes,
Yes?
we had a lab dealing with it.
Well, you're fortunate. I'm going to download Octave myself, and that way I can, if there are differences, I'll find them.
The biggest one so far is that you'll have to download like a symbolic package for Octave if you want to use any of the Sims functions.
Okay, fair enough. I mean, I don't think I really need to, but I appreciate that. All right, we've got that. I was going to just show you this. I think I did this class, but I'm not sure. If I create a vector, say x equals 1s, let me do it this way. This is, I think, called concatenation. If I have 1s, 1 by, say, 100, and then I have 0s, 1 by 156. This is a basic pulse function. Are you with me on this? I can show you it. If I go ahead and plot x, you can see it's basically a pulse function. That's all it is. So if I want the DFT of that, I can call capital X is going to be FFT in MATLAB of X. Now this is going to be the raw DFT. And then if I get that, and I'm going to plot ABS of capital X. Where'd it go? That's not very useful to me. All right. Now, I think I showed you the FFT shift, didn't I? Class? Yes?
Yes.
I'm going to do it anyway. I'll call it XS equal to FFT shift of capital X. And then now I shifted everything. And here's the deal. That still is not centered at 0 hertz. That's centered right smack dab in the middle of the range from 0 to its highest peak, which is 256 values. So what you have to do is go ahead and adjust that. And I think I did this last time, didn't I? Do you remember me doing this or not? Anybody?
Yeah,
I remember.
Yeah, I remember.
All right. I'm going to just say this, that if I go ahead and I take, and I want to get XX as equal to the IFFT of capital X. Now, that's not the shifted one. That will work. And I'm going to try it. So if I do that and then do the plot of X, just to be sure.
Hey, Dr. Baginski, I got a stupid question for you. So the reason you're plotting the absolute value, is that because you're wanting to look at the magnitude of the waveform?
I only want magnitude. The phase we could look at in a different plot. Remember, these are complex values. They have real and imaginary parts. So
Okay.
the typical way to do it is plot magnitude, and this is the frequency domain X, of X, and then below it phase. That's the way they always do it. And if you're wondering how to plot phase, if that's, well, it's just in MATLAB, I believe it's angle. Let me just try this. It's either angle or phase, and in different versions, it may be different things. So it's the angle of, if it's X of, say, 2, the second one, that's the angle in radians.
Okay.
And if you wanted to plot the total angle, then you would take, you would just do this. You would plot. And then it should pop up right there. Oops. Sorry. I got to plot the angle. Sorry. Plot angle. And that's ugly, but that's what it is. You follow me on that?
Yes.
Okay.
Thank you.
All right, next. If you don't mind hanging around, I'll keep going. We got 5 people yet. All right, the next part of the homework here this is MATLAB. And I give you, there's the adjusted, I ask you to do these 3, right? Class.
Yes.
These are straightforward. It's just like I did today. You can do those really quickly. And by the way, are you using GroupMe? I haven't been on there in a long time.
Yes, a lot.
What?
A lot.
Is this helping with this class?
Yeah.
Yeah, I find it helpful.
This is nice.
I mean, if I need to get in there, if there's a problem, and I don't care really, if you want me to, I'll jump on GroupMe if there's questions that everybody has, and I'll address them there. And you don't have to worry about it. You can talk however you want about me or anything. It doesn't bother. But, matter of fact, the provost told us all on a Zoom meeting that all your students know GroupMe, and they don't want you there. And I thought, okay. Better I'm not there. But if just make sure you tell me if there's a question so I can address it and try to get the answer to everyone, all right?
Okay.
Because I don't know how you guys are doing. Are your other classes going okay, by the way?
Mostly, yes.
Now, are you posting this to GroupMe, this video?
I'm uploading it to YouTube again, just as the next lecture in the series. So.
Perfect. I thank you. And I have to answer one email because this is kind of important. Whenever I get something from the associate provost, I know that something's up. It's probably about classes and what they're thinking about doing. I'm trying to move that here just for a second. Okay. Oh, and I'll put this back over here. So what about the next thing? This is I'll tell you where I'm going with this. The next thing I'm going to talk about is windowing, but is everybody basically good with all the homework up till now? Good?
I feel pretty good about it, at least.
I'm pretty good about it.
I need to, I briefly went and did a lot of the homework. It's just I haven't fully completed several of them. So
There's a lot of redundancy. I mean, the same principles are at work over and over again.
Yeah, I usually like to try and do a few problems by hand before I do everything on MATLAB and all of that.
Yeah, and it pays dividends to do that. Now, I'll tell you what I'm going to do next, just to give you a peek. You know how I told you that that if you have an ideal bandpass filter, you get something that is a sinc function that has an existence for forever. So it's not something you can really do in a real-time filtering operation. Do you remember that?
Kind of.
Yeah.
Kind of. Let me just put it down. Hey, I got to take this call, all right? Hang on for about 5 minutes.
So the email said it had some confidential stuff. I'm not going to know how to include that in the video. So
There wasn't anything in that email.
okay.
Yeah, he wasn't looking at the actual substantial email. That was just the one asking if they could give him a phone call.
It may be good to try and block out those emails.
Yeah, I mean,
just like blur the addresses.
Yeah, that would probably be a good idea.
I don't know how you do it though.
I don't know either. Hmm.
But he did say the homework, I mean, the test is not this Friday, right?
I don't
It
think,
had better not be.
I hope not, because like what
That
he's,
would be a huge curve.
That would be brutal.
yeah, I
I agree.
think it's Friday, but
I'm definitely kosher with the 2-hour print off your own test, scan it back to him. That seems fair, but
Yeah.
Yeah.
was I right? Like when I said e to the positive j omega, that was the right answer, wasn't it?
like wait a minute, and then you rewrote it, and it was the same thing. Yeah.
Yeah, I'm still confused on how to like come up with these equations by hand. So like I need to get better at that before I like jump into the MATLAB, and because basically I'm just writing a bunch of code that I don't know what really is going on. You know what I mean?
Right.
Mm-hmm.
Like after my thermo test, I'll probably be working on that some before. It's due on Friday, right?
So the part 1 of the homework is due on Friday, and I don't think there's any MATLAB for it.
No, but like it wouldn't
But then,
the rest get knocked out because like he goes over the entirety of part 1 in the video. Like,
yeah.
it's
Yeah.
all there.
Part 1's nothing but MATLAB, correct?
The written
No.
work, and then part 2 is the MATLAB. Like
Yeah.
Yeah, part 1 was what he just did in class. Essentially, he just answered all 4 of them or whatever. So,
But I'm pretty sure that with 1B, and I'm probably gonna put this in the group me, I'm pretty sure we're supposed to like plug it into that transfer equation.
I mean, he gave us the code for it, and so I just think you just stick it in and like take the graphs and stuff. So, or did something?
Not for part 1.
No, for part 2.
Yeah.
So have any of you guys done like the solving the circuit problems with Fourier series or the Fourier transforms? Because in the book, it talks about the transfer function is different than it is with the Laplace transform.
No, I don't distinctly remember any of those for me at least.
yeah, that's a 10-4 negative.
Well, I mean, I know he covered it in the lecture. I don't know if he actually gave any homework on it or not.
It's been a hot minute.
Yeah.
I couldn't tell you. I don't know.
The only circuit stuff I distinctly remember is Laplace.
Right. And the
Yeah, that
op
was-
amps with Laplace.
Yeah, that was the same here. All I remember was where we were converting like capacitors and inductors into their like Laplace equivalents, and then using that to solve.
Mm-hmm.
Right. You think we'll have a quiz this Friday? I don't think we will.
No. I think he's completely forgotten about them.
I don't mind that. But
I'm sure that the quizzes have been replaced by the homework.
That's what I thought he was doing.
Okay. I think that explains it, because like the way it sounds like on the syllabus, it looked like we're going to have both quizzes and homework. But I think
Well, he did that just to use your past quizzes.
like the past.
Right. Yeah. I think he originally was planning on giving a weekly whatever, like computer lock quiz or whatever.
But then
but now he's realizing that he's probably not going to be able to use that because it has to be multiple choice. So he's just going straight homework for quiz grades from now on.
Yeah, which makes sense because multiple choice would be hard with these kind of problems.
Like that would be really, really bad.
I mean,
think about it. It's you would get no partial at all. So and he would either have to give us like A, super, super easy questions, or B, have questions with a ton of parts in them. Some of them don't have that many parts to it, really. And like you would have to put in symbolically, and I don't think you can get numerical answers. So yeah, not the greatest.
Yeah, I have a feeling if he was forced to make it multiple choice, that the test would be ridiculously impossibly hard.
either like super easy or super hard. There would be no in between. So yeah. I wonder what like questions is going to be, what like level of difficulty, because like the ones that he said, oh, this is the level of difficulty you should expect, it wasn't that hard. Because like the DTFT transform, because like if you knew the properties, I think you should be fine. But I don't know. Weird stuff.
Yeah, I'd feel bad jumping ship here, but I kind of want to just go do the homework because I think between his explanation today and the video lecture, I feel like I can do at least part 1.
I'm back if you're here.
Oh, well, there he is.
Butcher box. All right. Any other questions, comments?
I have some questions about some old previous homework. Not sure if you got an email, but I had sent you an email with some questions about like circuits with the Fourier series and.
All right, which one? Just tell me where they are. This is Fourier series problems.
It was actually like in the video, I noticed whenever you were deriving the transfer function for, you know, solving a circuit with Fourier series, I noticed whenever you got the transfer function, it seems like you sort of ignored the voltage source. And I read in the book that it says
no. If transfer function is a ratio of output to input, it has nothing to do with the actual voltage, right? Transfer function is a ratio of the output voltage or the output, whatever it is, current or voltage, to the input. So it has nothing to do with the source itself.
So the source voltage wouldn't be the input?
It is the input, but the transfer function is a ratio of output to input. It doesn't matter what the source voltage is, right?
Okay. Well, I was reading in the book, I don't remember what page it was, but it was saying to replace the voltage source with 1 cosine omega t.
They're just adding a source and they want you to find the output.
Okay.
That's all. I'll try to use this tablet.
I guess I had a random question off topic. Like you said, butcher box. Like I've been curious about that, how it works, and is it worth the money or?
Fantastic. That's all organic, free range cattle or pork or whatever it is. And the more you read about this stuff, the more you're going to see it's probably better to eat as much organic free range stuff as you can, or go fishing for yourself or hunting, because the amount of crap that is in things that shouldn't be in our beef and stuff like that is pretty horrendous. And I have friends that are over in, I am in horticulture and animal science, poultry, people in poultry. You don't realize how much stuff's in those animals. They don't even allow certain things we do here in the US to be done in European countries or in India. And it has a lot to do with the GMO foods, the genetically modified organisms that they use. But that's for another day. I'm not an expert in this.
I was just curious. Like I know I thought it was kind of pricey, but I was wondering if it was
Butcher box is very reasonable. It's cheaper than the supermarket half the time than the stuff, the regular steak.
I might check it out.
Yeah, sure. I've been fooling around with an iPad, but I'm not going to put it in to use for us my paper. Let me try this though. I'm going to try to get over here and try to answer any questions you have. So then I got to cast the screen. This is a virtual office hour. Never have done this, never really want to if I don't have to. I got to share this screen. Can you all see the a screen up here, class?
The
Yes, I
OneNote?
can. See.
Yeah, I see a,
Yeah.
a blank screen. Yeah.
Tests. Okay.
Mhm.
So what are the questions you have?
I was trying to pull up that email that I had sent. I don't remember exactly what the questions were
All right.
because it was a while ago when I sent it.
Is everybody on here in Auburn right now? I see Jeffrey, Spencer, Nicholas, Christopher, and Lydia. Are y'all in Auburn?
Yeah, my wife and I bought a house here in Auburn, so I live here.
Jeffrey, are you in Auburn?
Same here. Yeah, me and my wife and daughter live in an apartment here in Auburn.
And Spencer? Are you there, Spencer?
You might not have a microphone.
He may have walked away too.
That
And
too.
you, Nicholas and Lydia, you're still in Auburn, right?
Yeah.
All right. Well, I almost feel like putting if I could get the whole class there, I could just put a bunch of tests out in front of my house. You could pick them up and take them. I can't. Anyway, what other questions do you have? I like the background, by the way, Lydia. I don't know where you got that one.
It's the virtual backgrounds. I think if it's a feature of Zoom where you can just like block out your background.
Yeah, I've done that.
It seems to not work when I do it. It like melded into my face and everything, like when Ruth tried it that day. So I think you have to have like a solid color behind you for it to really work well.
Is that right?
And since I'm in the living room, I've got like my door with the sunshine coming through and everything. So it's all different colored. So it messes it up.
I had a background on, and what it does, because I got frizzy hair, it like cuts out part of my head sometimes. That doesn't bother. Anyway, so questions. You look fine in that. I mean, your videos, you've got a good camera. Oh, what other questions?
So I have one question. It was in regards to the notation on the Fourier, the one-sided cosine Fourier series. I noticed in the book, they don't do the actual 2 times the magnitude of Cn. They just do Cn times the cosine.
Whoa, hold on. I think I know where you're going, but you're not saying this quite right. You're talking about a Fourier series analysis problem. What you're saying is, in general, if you have x of n, right, or x of t, pardon me, x
Correct,
of t, x of t, from there, if it is periodic, then we can go ahead and make x of t equal to a summation of c of n from n equals minus infinity to infinity of e to the j n omega t.
Yeah,
right?
that's the complex.
Yeah, I mean, but that's the exponential Fourier series. Now, if you want to, when we did this in class, we can create a single-sided Fourier series, which will be equal to C0 plus the summation from n equals 1 to infinity of 2 times the magnitude of C of n times, that's magnitude of C of n, times the cosine of n omega naught t plus the phase angle associated with C of n. You remember doing that?
Yeah.
That's where the 2 comes from.
Yeah, well, the book doesn't have the 2 times the magnitude of Cn, and I was just curious as to why the notational difference.
Are you talking about the trigonometric series?
No, the single-sided cosine series.
Yeah, but they have to. Give me a page number. They have to have this as a phase angle, and the magnitude has twice the magnitude of this value of C of n. Has to. If you show me a page number, I can tell you what they're doing.
Yeah, I'll give you the page number. It is
That's pretty cool.
Yeah, so yeah, it just phased me all out.
What page number?
213, top right. And that's where they use that equation to do the circuit analysis with the Fourier series.
You see where he has A minus JB, BN there? You see where it has angle of C of N and stuff? And if you look, he's using, and I don't use this is the trigonometric Fourier series. And if you look on page 209, all right, you can say there he identifies A0, A of N, and B of N. Oh, that's for even symmetry. Sorry, let me get the general form of it.
Oh, here, yeah, it's also on 202, bottom left.
It's 206. Yeah, but the thing is, their definition of C of N is based on A and B.
Oh, yeah, okay, I got you now.
Our C of N is not. Our C of N, remember, comes from what? The C of N that goes here is C of N is equal to the integral from 0 to pi, or 0 to t of what? 1 over t times the integral of x of t times e to the j minus j n omega naught t dt, right?
Yeah, so they expect a trigonometric series.
They have a different definition. They don't use this. They use first the sine of n omega naught t and then a cosine of n omega naught t to get an a and a jb. So don't worry about those. Don't worry about that.
Okay.
I don't mess with that.
So one other question I had is at the top of page 213, when it was saying use the voltage source as 1 cosine of omega t.
He says if you're going to do a circuits problem, you have to have a phasor input voltage. You see how it has a magnitude of C of n cosine of n omega naught t plus the phase angle, right?
Right.
All right. Well, what is that in terms of a phasor? That's C of n at the angle phi of n, right?
Correct. Yeah.
So what he's doing is, and we did this too, he's using a standard circuits steady state kind of response. And he has, let me just explain this. This one is the one you actually should use this. Now, if you take a look at that, that is x of t, right? It's 2 times C of n, magnitude of C of n, cosine of n omega naught t plus the phase angle. Correct, everyone?
Okay.
Now, if you feed that into a circuit and get an output, the circuit is going to have a transfer function, h of omega. That's V out of omega divided by V in of omega. It's a ratio, right?
Okay.
All right. Now, if I take V in of omega over here, now I get V out of omega, right?
Okay.
Now, this is for all frequencies, but if we have individual frequencies, what we do is take this and turn it into a phasor. So then x of the phasor value, remember what would happen is you would have C0, right? And then you would have plus, and then you would have a summation from n equal 1 to infinity. And these would be phasor terms. It would be 2 times the magnitude of C of n at the angle of C of n, right? This is the angle. Now those are phasors, right? They're at each frequency. I mean, the frequencies will be different. Here, we know that omega will be equal to n omega naught, where omega naught would be the fundamental, right?
Okay.
Y'all with me now? Everybody on this one? Now that's the phasor. So if I take this and I multiply it by h of omega, it'd be h omega at each one of those frequencies. So it'd be this right here times h of magnitude of h of n, h of n omega naught. That would be the magnitude you'd have to do first. And then you have to plug in a phase angle in there, plus the phase angle of h of n omega naught. And then you would take it back to the time domain. Now, I didn't even put the h of 0 here, but I'll show you what it looks like. If you go back to the time domain, your value for the output would be y of t would be equal to x, really a cn of 0, or it'd be, it would be h of 0 times c of 0, that's the DC value, plus the summation from n equals 1 to infinity of 2 times magnitude of c of n times magnitude of h of n omega naught. Then it's going to be times the cosine of n omega naught, right there, times t, plus the phase angle of c of n, plus the phase angle of h of n omega naught. And I did this in class. How many remember me doing this in class? We got 1,
Vaguely, yeah.
2, 3. Okay. And so that's how that comes about. It's a very powerful technique.
Is it used commonly in when solving?
That's exactly what LT Spice does. All these things basically take any signal that you have and represent it as phasors at different frequencies.
Okay.
I mean, yeah, they can actually do something that would be a fast convolution, but this is something that it helps you understand when you do circuit analysis with MATLAB. If you want the output, well, we can get the output fairly easily. We can actually plot that. All right.
Okay.
Other questions? Nicholas, do you have any questions for me?
No, I think I'm good right now. I need to go back through older problems more today. So.
How about you, Spencer? Do you have any more? Jeffrey?
I'm kind of in the same boat as Nick, I guess. I just need to review more of the stuff we did, way long time ago.
All right,
I'll be
Chris?
more prepared for the test.
Yeah, and that's another thing I wanted to talk to you about. This Friday, Lydia and Nicholas, everybody here, remind me that we're going to schedule a test date. All right. And by then, I've sort of decided, I'm letting other people give tests. I'm getting feedback about problems. I'm not going to give them multiple choice under any conditions. I'm going to have you do your work and have you get it back to me in some time window. And I'm not going to give you an absurdly difficult test the way some of these professors, Riggs will do that too. He'll come up with a test that's right out of hell. Something that nobody can solve, not even him. And he'll give it to people just to see what they can do. You better not share that with Riggs. Now that I think about it. But it's going to be a time test. In fairness, you're going to have a lot of things available to you. So I know I've got to create something that some people can't use, Wolfram Alpha or Mathematica or MATLAB or Mathematica, MathCAD, and there's probably more that I'm not listing. It's got to be something that's not easily done with those. That's sort of my take. And it'll be fair. Other questions?
If you have time, I have one more question.
Yeah.
I was going to see if you could explain how to do the derivative method on a Fourier or on a waveform doing the Fourier series, but do it where you have to do the derivative method twice, sort of like when you have to do it once, then you have to break the functions apart because you have delta functions at each step.
Yeah, well, oh, you wanted to, so we'll do it. Let me see if I can actually draw something that's with this that'll be a little easier to understand. First, I'm going to get a graph. Oh, come on. All right, now I'm going to draw something. I'm just going to call this tau. I'm going to call this sigma, and let it repeat itself every t. That would be the period, so it'd repeat itself. And make the height here just equal to 1. All right?
Yeah. Quick question. So this one, when you do the derivative method, there's only, no, I'm sorry. You're right. You have to do it twice on this one.
You first get this. First derivative is going to be this. It goes to 0. And this is just 1 over tau, the height. Then right here, you're going to get a negative impulse. This is going to be minus 1, really, minus delta of t minus sigma, right? Y'all follow me? It goes from 1 to 0 instantly. So
Right.
that would be a delta. And this thing repeats itself, agree?
Yes.
Yes.
So I make this one series, call this x1 prime, right there. Okay.
Mhm.
Then I take another derivative of this thing. When I take a derivative of this, I get an impulse here that's up. It has a weight of 1 over tau in front of it. Right? That's a delta of t times that. And then right here at sigma, I get another impulse. It's got minus 1 over tau is its weight, right?
Wait, is that at sigma or is that at tau?
Tau, pardon me.
Okay.
I'm sorry. You're right. So this is a tau, my bad. Now this is just x1, this one right here. These two derivatives, I mean this delta functions, now I'll call that x2 double prime.
Okay.
All right, let's get the Fourier coefficient for this one. Well, I know that this thing is in general, the Fourier coefficient for the first one, C1 prime, would be 1 over t, the integral of that function, which is just minus delta of t minus sigma times e, what now? Oh, e to the
minus j n omega.
And omega naught t dt, right? And that, I'm going to just go from 0 to t. Is everybody okay with that?
Yes.
All right, this is just for the first, the x1 prime. So now when I get that, you can see this thing turns on at t equals sigma. So this C1 prime here is going to be equal to minus 1 over the period t. And then it will be just e to the minus j n omega naught times sigma. Agree?
Yes.
Okay. Chris, were you the one who asked about this?
Yes, sir.
Are you with me?
Yeah, I'm with you.
Now I'm going to divide it by j n omega naught because I took one derivative to get there.
Okay.
For this one, I've taken 2, right? Why don't you tell me what this is? Somebody tell me what this is going to be. This would be C, sorry, C2 double prime. What's that going to be? I know I got a 1 over t in front of everything, but what's it going to be, guys?
Shouldn't it be e to the minus j n omega naught with t replaced by
Where's the first one turn on?
at tau?
0, right? This one is at 0, isn't it?
Oh, sorry, I didn't see that one.
I got somebody sending me a message from our class. Hold on. Give me 1 second. I gotta grab this thing. There we go. Oh my goodness. Oh, this thing's a pain. Hi, my name is, I'm an acquisitions editor. Oh, never mind. That's not important. Um, all right, back to this thing. Y'all agree that the first one is just 1, it's e to the 0, right? And then it's what? Minus e to the minus j and omega naught times
Tau?
tau.
Mhm.
All right,
And shouldn't there be a weight out front of 1 over tau?
there is right out
Okay.
here. I didn't put that, but you're absolutely right.
Okay.
Should be right there. It should be a 1 over tau, and I apologize for that. Now, there's one last thing we have to do. What do we need to do?
Where did the 1 over tau come from?
See the height on these things? They're 1 over tau. Remember, when we took the derivative, it's the slope of that line. So it's the rise is what?
I got
Line
it.
divided by the run tau, right? Okay. Now, there's one last thing. What do we have to do with this, guys?
Divide by
Yeah. Go ahead.
Squared.
Squared,
squared.
because it was the double derivative.
All right. Then what you end up doing is add C1 and C2 together, and that is your coefficient of the e to the j and omega naught t. Agreed?
Okay. Not as bad as what I thought it was. So, all right. Thank you.
They're only bad if you only understand part of it. Then you get confused as heck. But if you understand the process and what you're doing, you can keep taking derivatives until we get just impulses and then find the C of n because it's a trivial thing to do. And then divide by j and omega naught to the power that has to do with the number of derivatives. Other things? How are you guys' courses coming overall?
Not bad. Honestly, this is the one that I'm most concerned about right now, but other than that, like, it's pretty good. So
This is in my opinion, it is the most challenging course because there's a lot of abstract concepts and there's a lot of things moving at once. And I just talked to Emmett Wynn about this. That if you're a good chess player, you're good at this, and if you're not, you're probably horrible at this. It's sort of I found this out. I shared that story, didn't I, about the kid I had who was a Federation master in chess. He became an international.
I think you did, yeah.
Yeah, you did.
His name is Stephen Muhammad. You can look him up. Muhammad. I'm so glad I didn't play that guy for money. That would have been an embarrassment. But I feel this way. I think this is much more difficult than calculus or physics or even digital electronics because there's so many abstract concepts that you have to deal with.
Yeah, I was doing really well up into the Fourier transforms. The discrete stuff. That's what started to give me a little problem.
Well, DTFT is really a Fourier transform, but it's for a sampled signal, and that's what makes things a little crazy. What else?
I'm kind of in the same boat as Lydia. Like, this is probably the class I'm most concerned about, although I have our first power test after, all online coming up on Friday. So that's been kind of a struggle trying to kind of teach yourself power since all we had is PowerPoint.
It's just circuits. It's circuits applied to three-phase. That's all it is.
So,
but I tell you one thing about Gross. He tries to throw you off balance. Don't get flustered. Power is not a hard course at all.
I don't think it'll be too bad, but he seemed to be fairly lenient for this test since he kind of figures all of us are kind of in a bind. So,
well, these are desperate. These are times that nobody saw coming. I mean, the provost's office and Jay Gouge, they're doing a magnificent job managing this whole thing just to get us everybody to have access to Zoom. By the way, my neighbors are teachers around here, a couple of them. And the school system in Auburn is going to go to all Zoom shortly. And when they do that, I don't know how much I'm going to have to get the highest speed internet possible.
Yeah, they actually just started. Like my daughter's a 7th grader, and they just started. Weekly meetings will start Monday for
Well,
the kids.
You know, this is data intensive. When you have video streams, especially if you're going to have a whole, say, like these meetings we have with the provost, we're going to have something, or we got like 40 or 50 digital streams back and forth. And the people with the lower internet speeds, you can tell they're talking to freeze, then all of a sudden it'll be garbled. And if it's just one-on-one, if it's like a Skype call, there's no problem. But the minute you put all the other things in the mix, that data, the amount of information they can carry, they can carry effectively is exceeded. So the providers, I have Spectrum, they come up with an algorithm to who gets the weighted bandwidth. You know, if you're at the high end, if you're paying for 300 megabits download, then you're going to get the lion's share of the information speed. I mean, of the available bandwidth for yourself. And other people just, they're going to make do with what's left.
Right. Yeah. So I know that actually my daughter at 10 o'clock had a Zoom meeting today with her teacher.